Hello, I'm Robert Walker and this is my presentation for my preprint, and as you can see the title is quite startling because the Perseverance rover is already on its way to Mars and NASA plan to return the samples to unsterilized samples to a facility on Earth by 2031. And yet it doesn't seem that they could do it even before 2040 unless they sterilize the samples, which is, I think that's what they're going to do personally. So I'm just going to answer, first of all, a very basic thing, that if you have not been following the planetary protection literature, you might think, well, Apollo did it. They seem to do it no problem. They returned samples from the moon. And as far as the general public is concerned, then they seem to have done it properly. But in the planetary protection literature, the Apollo sample handling is used instead of it as an example of how not to do it. It's now considered that they didn't protect Earth at all. There was hardly any protection, and it was largely symbolic. So we can't do that. We can't just follow their example. It had no peer review at the time and no legal scrutiny. The legality is questionable and it was rescinded, so it couldn't be used anyway. So that's basic. That's basically bringing people up to speed who don't follow the planetary protection literature. So then, if you follow the planetary protection literature, it will still seem to be possible, but barely so. Because if you know, for instance, Owen et al.'s paper from 2019, they estimate the timescale as 11 years to build the sample receiving facility. And that would seem to be something that you could do by 2032, say, if you started next year. And then, again, if you haven't been following the literature, you might well think, or even some people who've been published studies of potential sample containing facilities, then they seem not aware of the requirements, the detailed requirements, and you might wonder, why would it take so long and take 11 years? So I'll answer that first, and then I'm going to explain why it would take even longer than that, and what's been left out. Basically, I'll just quickly describe that bit and then I'll go explain the other bit. So the legal process is, they assume in these studies, happens in parallel, and that takes 8 or 9 years. But that's very optimistic. You have to assume, they just analysed the US process. We would have to go through a parallel process ESA would have to go through a parallel process in Europe, in Canada, in the United Kingdom. They would have to be all on board. Then the international treaties and the World Health Organization would get involved at some point. And so all that would have to be coordinated in a massive way, starting in 2021. And then if you're very optimistic and that all those things work, and there are no serious objections, and they all in parallel go through their legal processes, and there are no problems, and there are no delays, then maybe you can complete the legal process on the same timescale before 2032. The 8 or 9 years seems very optimistic. And they say themselves that this is like the bare minimum. But then if you looked at it that way, you would think that still it is possible by then. However, what I discovered is that before NASA can start the build, they have to do an enterprise service review and an enterprise architecture review. They have to do that for any project that's going to cost more than $1 million, and the Mars receiving facility, the latest figure is a bit under $500 million when they did the last round of getting proposals for how to do it. So you're talking about a very expensive facility, and NASA will not start building such a thing until they know what they have to build and how it's going to be serviced. So they won't know what they have to build until they complete the legal process. Because it's not like with the Mars sample return studies, then the remit is, what's the best way to return the sample to Earth? And then with that remit, they then design this technology, and then that would be the technology, presumably, that NASA would use for the most recent Mars sample return study, and then they could start the build based on that. But they can't, because when you go to the legal process, then NASA is now the proponent, and they're saying this is what we plan to build. As they go through the legal process, then being scrutinized by experts in many different domains, then they could look at this and they could say, but you've missed something out, or an extra precaution is needed, or no, this is not quite right. So NASA can't know what they're going to build until the end of the legal process. And what's more, they can't know that it will be approved until the end. That is that is assuming the conclusion of the legal process, and you can't do that. The whole point in the legal process, you have to prove that you can do it. And so NASA, there's no way that they're going to start the build until they know that they have legal permission to build it. So the two have to run one after the other. And so then when you add the 8 or 9 years to 11 years, that's the most optimistic of all, you get to 2040. So that's the central point. And then, so that's the main thing. Have I made any mistakes there? Is there anything I'm missing in that basic argument? So I am not stopping the sample return. I'm just presenting here things that are certain to come up. There's no way that you go through the legal process, they ignore these recommendations of the European Space Foundation study and the requirements on the build. However, it is worse even than this in terms of the timeline, because after looking at this carefully and closely, the required technology doesn't exist. And again, you might be very surprised, because you would think, well, it's quite simple. We just return it to a biosafety cabinet in a corner of, we don't even need to build a new facility, just an ordinary biosafety cabinet, put the sample in there, manipulate it with gloves. You know, you look at how they did with Apollo, and you think that you can do it that way. But and that was indeed how astrobiologists thought about it in the 1990s. But this is no longer how they think about it, because the requirements have become so stringent as a result of looking more carefully at it. So the problem is that we're not containing a known hazard. We have to design a facility that could be used if, hypothetically, through some magical way, you could get a sample from a Mars planet orbiting a star in the Andromeda galaxy. You would use the same precautions, because we know nothing about the life on Mars. We don't know that it's related to terrestrial life. It could have been independently evolved there. Or some of it could be related and some not, and the related stuff could have come to Earth, but panspermia, despite everything you read, it is not proven that life has been transferred from Mars to Earth, so we can't assume that. And so then if you look at the minimum size, and then the example I use is mirror life. Suppose that Mars had mirror life and normal life coexisting on the planet. And as far as I know, nobody has ever used this in planetary protection discussions, that particular example, although synthetic biologists are in the process of trying to make mirror life in the laboratory. And so they discuss this. And they say we must not make it, it is totally unacceptable for mirror life to escape from the laboratory. So if we do make this mirror life, which will take probably quite a few more years or decades, but if they succeed in the process, they have it all mapped out, but each step is difficult. If they succeed in this, they will make sure that the mirror life can't escape from the laboratory, because it just wouldn't be safe for the terrestrial environment. And the reason is because most terrestrial life wouldn't be able to eat it. And so it would have a huge competitive advantage, and you could end up with the oceans covered with green sludge of, for instance, some photosynthetic mirror life, and nothing can eat it, and then it sinks into the bottom of the sea. And so they paint out, it doesn't look pretty, the future of the terrestrial biospheres if mirror life gets into it. So we have to be very careful. At this point, we don't know that Mars doesn't have mirror life on it. And so, and this again is going to come up is sure to come up, because you're going to get synthetic biologists looking at looking at the process as well, and they will bring up this and say, well, we've been looking at mirror life, and what happens if you return mirror life? So again, I'm not introducing anything new. It's just that I'm joining together different disciplines that don't seem to have been talking to each other. So then, if we look at the 2009 study has the requirement of 0.25 microns, 2012 study, then in between the two, they discovered these filterable bacteria that go through 0.1 micron nanopores. And so they set a requirement of 0.05 microns. Anything above that is unacceptable. You can't return even a single microbe at that size, above 0.05 microns. It can't escape from the facility under any circumstances. So then if you go and look at the various designs, they all use ALPA and HEPA filters. They're not tested down to that level. There are no commercial filters available that are tested to contain even a percentage at that level. And then if you try and look at the experimental filters in laboratories, then I found this one, which it was designed to try to contain every single virus of COVID-19, of the virus particle SARS-CoV-2. And our current filters don't do that. They just work in the ICU units. They work by reducing the viral load to such a low amount it's no longer infectious, because you need many viruses to infect someone. But a single virus would be able to get through a HEPA filter on a small droplet. And we don't have any filters that can keep out a single SARS-CoV-2 virus. And this test filter in laboratories, which is not available commercially, can filter out 88% at 50 nanometers and larger. So this means that the technology does not exist. That is needed for this facility. And then, to add to that, the periodic review may reduce the minimal size of particle that can be released. So we already have the possibility of RNA world cells that don't use proteins, that don't use a single informational biopolymer, that are and that don't have the very huge ribosomes instead of ribozymes. This is theoretical. We can't make them, these RNA world cells. There are attempts to try and evolve them from scratch in the laboratory with a bit of assistance. They're only at the very early stages. There's been a lot of research into the possibility of RNA world life, which builds on them, and there was an earlier estimate in 1999 that an RNA world cell could be as a long and thin one again, could be as narrow as 0.14 microns. So it's not impossible that if this was alien life, that they would be able to go through a 0.02 micron nanopore. And so this is something that would need to be looked at very carefully, whether that is possible, bearing in mind the research since then. And if it was, you can expect that this unacceptable region to go down to 0.01 microns. So we certainly need to review 8 years later. They said that it's so startling, the reduction from 0.25 to 0.05 microns, and they don't think it's going to come down further. That was written in 2012, but it needs review to see if these requirements are changed as a result of later research. I think that it's very likely will be reduced below that. Anyway, so that needs to be done. So all that needs to be done before you start the build. So before NASA can start the build, they need to complete that review to find out if the requirement is 0.05 microns. And then they have to design the technology which doesn't exist yet. They then have to design the building based around this non-existent technology. And then they have to work out how to service it, because filters typically need to be replaced every year or so. So you need to work out how to do that as well. And remember, the best optical microscope can only see down to 0.2 microns. This is well below optical resolution. And just a tiny crack or mistake in the weld or something that could let something through. So this technology, so as they go through the legal process, then indeed it's hard to see how they could get far into the legal process until they have the technology at least mapped out. So that would add on to all of this. Indeed, even if you didn't have to do the legal process, you're talking about the mid-2030s or late 2030s before they can complete the build, after having first gone through the process of making the necessary technology, of developing the necessary technology for the build. You've got to add that, the time period to develop the technology, onto the time period for the build, and then the time period for the build might take longer as well, depending on what you have to construct. And then you add the legal process to all that. So unless I've made some major mistake here, it seems just impossible for them to return the sample before 2040. Indeed, it could well be late 2040s or later, once you think about the need to develop the technology before they start the legal process, the extensions of the legal process, because you've got to do it in so many countries simultaneously, and then you've got to complete the build. It's just not feasible. So what do they do instead? So if I've got that all correct, then what do they do instead? So one possibility is they just sterilize the sample. Oh, I'll just quickly say one thing. So first of all, I'll quickly say, because any of you who are Mars colonization enthusiasts, then you may well have heard Zubin's arguments, or you might just intuitively think, first of all, that Mars is sterile, or secondly, that any life that's been on Mars has got to Earth already. So I'll quickly answer those 2 points. So first of all, these are the Curiosity brines, and they discovered this is actually on the liquid at 0 degrees centigrade, and this is liquid at 5 centimeters below the surface. And as you can see, it discovered liquid pretty much most of the year that is liquid at the surface, but it's just discovered it indirectly through humidity changes as it goes over the sand dunes. So if the water does exist there, now it's too cold for terrestrial life, but it may well be that Martian life can have faster metabolic processes at lower temperatures. Also, even for terrestrial life, you're talking about slowing down the metabolism. If it can freeze into a glassy state, so it is safe even at very cold temperatures, then some terrestrial life may be able to reproduce from Antarctica. Then they can reproduce at very, very slowly. They can have a division time of centuries, millennia, maybe even hundreds of thousands of years. That research is controversial because it's just impossible to measure it over those timescales and to do the experiments. How do you determine if it's going to complete splitting over, if it's going to be able to do that over 100,000 years, say? But on Mars there would be time. So you could have very slowly reproducing life there, but you could also have, but in terms of forward planetary protection, then they just say that if terrestrial life gets into these brines, then it's not going to be a problem over human timescales into the future, even if it reproduces, it can reproduce over thousands of years, then that's not going to affect anyone over the next few thousand years or 100,000 years. And that's why they basically say it's okay if the brines are very cold. There's a sharp limit to water activity that there doesn't seem to be possible to have life if the water, if it's too salty. But if it's too cold, it's just a very slow change, that it gets longer and longer lifetimes, longer time And then, as well as that, the terrestrial life and Martian life, using the chaotropic agents such as perchlorates, may be able to speed that up. And then we can also get biofilms which retain the water from the evening through to the daytime. And so there could be life there by both those methods, either through the biofilms or through life that can withstand very low temperatures. And there are various other possibilities, and some would be more easier habitats for life than this, but this is a very clear one because it's pretty much proven that these brines do exist. And then if you look at the Viking labelled release, then it's offset by 2 hours. The evolution of the carbon, of the labelled carbon dioxide or methane, carbon-containing gases, is offset by 2 hours from the warmest time in the day. And that's very hard to explain through chemical processes. A small offset, yes, but offset by 2 hours to the spike is very hard to explain. So there are astrobiologists who think that perhaps Viking discovered life in the 1970s, the Viking landers. So, and then there's another thing that I'll go into that in another video, but it's my own idea of what you call it, a swan song Gaia. And that's the idea that Mars had a swan song biosphere, which eventually, when it got too cold, if it had life early on, it got too cold for life. The normal idea would be they had a swan song biosphere for a few, maybe a few 100,000 years or millions of years, but eventually it got too cold and the life was gone. So swan song biosphere is when the relics of life, but it's not extensive, but there's some life still. But I argue that it's possible that Mars actually is producing enough carbon dioxide to maintain liquid water on the surface and lakes all the way through to the present. We know it is emitting carbon dioxide all the time, and the reason that we don't have liquid water there now is because of photosynthesis, which would take carbon dioxide out of the atmosphere and maintains the Martian surface in a barely habitable state, where it would constantly maintain it at the triple point of water, where there is which is the situation it is in right now. And then sometimes the big output of carbon dioxide would get liquid water, or changing of the tilt of the Martian atmosphere, you get liquid water for a while, but very quickly the photosynthetic life would take the carbon dioxide out. So what works on Earth to keep Earth's biosphere from getting too hot, on Mars it would keep it very cold, and keep it so cold that it's only barely habitable for life, but not enough to completely stop life. So the idea is not completely new to me. There's the idea of the same process happening through abiotic photosynthesis and other ways of sequestering carbon dioxide. That's been published. All I did is add the idea of biotic photosynthesis to this suggestion to explain how there could be so close to the triple point. So if that's the situation, then all this could make it very likely there is life on Mars in very small quantities, being kept at barely habitable, and itself a feedback process that makes it very difficult to spot because it keeps itself in a barely habitable state. If this is correct, then it wouldn't matter very much how much carbon dioxide produced. If it's less than a certain amount, then all Mars-like planets throughout our galaxy and all galaxies would be very common to be in the same state as our planet. And so it being in this triple point state would be normal for a Mars-like planet, because this process would tolerate quite large variations in the amount of carbon dioxide being emitted. So, and these just some intriguing observations by Curiosity, an increase in oxygen in the summer and decrease in winter. And this could be explained if there are really quite large amounts of biomass in these biofilms. It's within the range of what is possible. It's beyond what would be normal for the driest areas in Antarctica. But if you do have these biofilms coming forward into the daytime and spreading throughout these brines, which we don't have in Antarctica and in the Atacama Desert, we don't have these brines just below the surface. It's because of perchlorate salts, which are very hygroscopic. And so if you take very optimistic, then it could even maybe explain this, or maybe it only explains part of it, or maybe this is something else. But it's a bit intriguing that you have that. And also, there's a weak correlation with how opaque the dust optical depth. that the more transparent the dust is from the dust storms, then the more oxygen is evolved. So that again, it all suggests there could be brines there. So then the point is that there is. So I hope I've just convinced you that there's at least a possibility of life there. Whether you believe all these arguments, at least it's an intriguing idea that there could be life there, and we can't disprove it. And this is I just focus on one of many potential habitats on Mars that astrobiologists have looked at. So you might have expected me to focus on the recurring slope lineae. Those may be caused by dust, they may be caused by liquid water involved as well. That's another possibility. But this is much more pervasive, and it would be right close to where Perseverance is, if it's correct. Now, the thing is that we don't have any samples of dust or salts from Mars. It's never been transferred from Mars to Earth. And there's no reason most terrestrial life couldn't be transferred from Mars to Earth. Only some very special, very hardy microbes would be capable of getting all the way from there to here on an asteroid, on a meteorite. And so, but the meteorites we have all come from 3 meters or more below the surface of Mars. And then if you look at the processes that cause it to be ejected from Mars, then asteroid impact hitting Mars would not throw surface rocks into orbit. It's below the surface. This layer on Mars, 3 meters below the surface, is believed to be sterile. It's just too cold for life there. Almost everywhere on Mars, unless possibly with the RSLs that I explained. If we were to hit one of those dead on, maybe if you hit just the right place, you find a source of life below the surface according to some of the models. So it's very unlikely that life would be transferred from Mars to Earth in the present time. And we don't know if it ever has been. And then, as I think I said before, if you've got two forms of life, ordinary life and mirror life, it could be just the ordinary life that's been transferred, if life was transferred at all. Maybe the mirror life, which would be evolving independently, didn't evolve the capabilities to get here. So first of all, this idea that Mars is sterile, so we don't need to worry. I hope I've explained about that. And then the idea that it's already got here. Again, we can't assume that either. So we can't bypass that. We can't bypass this process. So then the possibilities. First of all, you sterilize it. So I'll just quickly talk about that, and then I'll stop. I think I don't want to make this too long. I'm going to do another. I want to stop at half an hour. So I'll just quickly say we can sterilize it, and the two possibilities are to sterilize it, and this is how you could sterilize it with a miniaturized X-ray, nanoscale X-ray emitters, and only at watts. I'll look at that in the next video, and whether we can do that now and the complexities of it will be much simpler. You wouldn't have, and that would just be like returning the comet and asteroid samples we already have. And then this is about ways that we could increase the possibility of returning a sample that is of biological interest. And then the other idea is return it to the Laplace plane, which essentially is the ring plane for Earth. If we had a ring system, then the particles would orbit in the Laplace plane and not in geostationary Earth orbit. And this is the phase space where particles release from a point in the Laplace plane. And this is a paper about using how in the Laplace plane is a place where you could dispose of satellites from the geostationary Earth orbit without any risk of debris from them going back and hitting these satellites in the orbit, the active satellites. It's an optimal place, and it's at about 7 degrees inclination. And then if you look at the evolution, and they also take account of the eccentricity, and they figure out that it would just be a safe place to be. So I recommend that we put it in. We return the sample to the Laplace plane above geostationary orbit, and then we would study it by telepresence there, and basically be doing a Mars mission to get to the geostationary orbit, where we send all the instruments up there that we would normally do from the that we'd normally send to Mars. We send them instead to above geostationary orbit, and we return it there. So I'll look at those. Those, I think, are the two possibilities of what NASA can do, and so I will talk about that in my next video, and I will stop here because I don't want the video to be too long. I said 20 minutes or half an hour, so I'll do that later, and I'll upload this. And so I'm very interested in comments. It's quite a difficult. It was a very difficult paper to write and research because it's so multidisciplinary, and that is why I'm particularly keen to get feedback from people who are experts in these various disciplines. You know, have I summarised research correctly? Is there any mistake I made? Is there any gap in what I've described? And so please, if you see anything, do comment. If there's anything I've got wrong, anything or any other way that it could be done, then please explain in comments or contact me at I'll put my email in the video description, and a link to the preprint I'll put there as well. So thanks for listening. Hope you found it interesting.